All right, now, so let's go ahead and talk about delta G. What is that G? Gibbs free energy. Now, back in the days, we have a couple of words that we use, but nowadays it is not very popular or said by the College Board. So back in the days, we'll say, oh, something is, we can talk about the reaction being spontaneous. And non-spontaneous. And we talked about this back in Chem 1. Yeah. Spontaneous, right? Now, so this will not be the official language from the College Board on the AP exam. Instead, they would say what? If it's spontaneous, they would say it is
so they just made it complicated for no reason.
Now, is it for no reason? I have no idea. I never really asked or to dig out why they changed the wording. But for us, for AP chemistry or freshman general chemistry, I would say, yeah, it's fine. Okay. Not going to make a big deal unless well, somebody please educate me how this is a big deal. But for us, in terms of our conclusion, it's not really a big deal. And then for the non-spontaneous, all right. So that's just the language. Now, and also something back in Chem 1, there was an equation that I told you all not to memorize. The delta G is equal to delta H minus T delta S. Now, this is an equation to determine, oh, by the way, I should say this. It is an equation to determine whether a reaction is spontaneous or non-spontaneous. And for spontaneous reaction, the delta G value is supposed to be negative, and the non-spontaneous is supposed to be positive. Now, I actually have an explanation for this.
Oh, they use spontaneous in the packet.
But I think they also say favorable, something like that.
Also on packet, so
yeah.
It also says
yeah. So now I want to make sure that you have a good understanding of why it is negative for spontaneous. There's a reason behind it.
Is it because if you plug in a negative number for S, you end up getting a positive value? So like, saying like don't memorize because logically whatever your S is will determine whatever your G is, right?
I mean, it's going to be both H and the S together. Okay. But my question is how come spontaneous is negative? Now, so let's talk about something that is absolutely negative. Well, how can we have a reaction that's absolutely spontaneous? Well, we need some help. We need to look at delta H and delta S, and they will have to be the driving force. Okay, remember the driving force? How they aid the reaction to become spontaneous. Well, if you want the left-hand side to be spontaneous, what do you want for delta H? Yeah, negative. Okay. So now, exothermic reaction, right? Exothermic. Now, let me stop a moment right here and ask and explain something. Between endo and exo, is it common sense to you that the exothermic reaction is more likely to be spontaneous?
What is spontaneous? What is spontaneous?
Very good. Say, if I take ice out from the freezer, put it on a desk right here, it's going to melt, right? It's going to happen without any of my help. That is spontaneous. Okay? But if I put the water back into the fridge, and that's a low temperature, right? It's going to freeze. And that would also be spontaneous. If I say, oh, can I take water out from the refrigerator, put it on a table, and then it freezes at this room temperature on this table?
No. do something.
Okay, so that means it is non-spontaneous.
If I'm pouring boiling water over ice to get it to melt, that's not spontaneous.
One more time.
If I'm pouring boiling water over ice to get it to melt, that's not spontaneous.
Well, if you put boiling water to ice, then essentially you're changing temperature. Okay, now we'll talk about those scenarios in just a moment. But let me go ahead and explain.
Exo is releasing energy, right? So it's
more likely to be spontaneous. It's a likelihood. It's not guaranteed to be spontaneous, but more likely. And the reason is this. If you remember your graph for delta H, what's the difference between endothermic and exothermic reaction? Endo is like this, right? And exo is like? And what is the main difference between these two graphs is that, well, for endothermic, it's likely going to be a high requirement of activation energy, while exothermic reaction, small amount of activation energy. So that's the reason why exothermic reaction is more likely to happen. Okay? Think about gasoline.
Oh, so that's why something.
Gasoline, you burn it. I mean, it demands activation energy, just a spark. You give it a spark, it's going to run by itself.
Because of the activation energy.
So exothermic reaction needs less activation energy. Okay, it's of course in general. Okay. And then what about delta S? Is it more spontaneous to be more chaotic, more disorder, or is it more spontaneous to be more less disorder? More disorder, right? Just look at this room. It was clean, and then it gets messier after time. So therefore, you want to have a positive. Okay, we have a more disorder. And I'm going to use green color to put a check mark next to these two because they are both the driving forces to make G negative. Okay. All right, now, so let's go ahead and change a couple of signs. And that's why I said do not memorize this. So what happens if they're both negative? What happens if they're both positive? Okay. So the delta H is still the driving force. But if the delta S is negative,
couldn't it be bigger? It becomes bigger. But how do you know it's bigger? Well, because if that whole thing is negative with the minus becomes plus.
Yeah, the minus becomes plus.
How do you know that the T entity is
the T is always absolute. It's in Kelvin.
So it's always going to be bigger than, like the T delta S will always be bigger than delta H.
Well, actually, not always. So we say this is spontaneous. This is spontaneous at low temperature. Why? Because the delta S is not cooperating, but you can make the temperature lower to minimize the impact of the delta S.
Yes.
And that is our ice freezing, the ice making process.
And what is considered like low temp versus high temp?
Well, then that's the calculation part.
Awesome.
Because by then you will have, you will actually set up an inequality. You want to make the right-hand side to be less than 0. You will have the delta H, you will have the delta S, they're both in the table, and then you calculate the T, okay? And speaking of this, you may also think about T is equal to simply delta H over delta S. And that will be at equilibrium. But if you want it to be spontaneous, in that case, it would be T being less than delta H over delta S. Okay, because you want to make the right-hand side to be less than 0. Oh, wait, hold on. Wait, hold on. Let me derive it. T is greater than, sorry. T is greater than?
I mean, yeah, you're not supposed to look at it after that. I don't remember after for like 20 minutes.
Greater than. Greater than.
I admit, Eclipse is underwhelming. We did not have a good view. It's just but we didn't get the totality of it.
Yeah. Okay. Or just go ahead and calculate this. Just make sure you set an inequality. Okay. And then for the third scenario, our positive delta S would be a great help, right? So you want to have so this would be a negative at high temperature because you want to have a big subtraction, okay? Delta H is not helping, so you want to have a big subtraction. You want to have the negative term to be bigger so that it becomes overall negative. And if it is positive and then negative, then they're both not helping. And that means it's going to be positive, non-spontaneous at all temperature, at all time. Okay?
So, okay.
All right, so changing temperature won't make it happen. Now, but I would also like to mention one thing, that if the reaction is not spontaneous, that means the reverse reaction is spontaneous.
Wait, for entropy, I know that solids have less entropy, but is there any way to increase the entropy of a solid without changing, like you know how like the molecules are really close together?
It increases temperature. If you increase temperature, it's going to increase its entropy. Well, not like exploding, but you just like think about this from a well, not much. So that's why the value won't be a lot higher. But what it does is that when you increase temperature, based on the kinetic molecular theory, it's going to move faster, but faster in a very limited sense. Yeah. Mm-hmm. Yes. Yes.
So does a solid that's bigger have more entropy than like does this have more entropy than this can, or does that depend on how heavy the two are, the mass?
It depends on the internal structure. Yeah.